remember what our trick is for dealing with a compound machine. To find the overall mechanical advantage, you just find the product of all the mechanical advantages of the individual machines that are stuck together to make the compound machine, right? So,
Wait. Well,
Take a picture.
I didn't know
oh,
No, but Ellie wanted to copy the question.
it's okay.
I know, but that's
still
a year
there.
ago.
And I will update these today. I'll put them up today. So we've got, let's see, the bicycle, the pedals. So everybody understands what's going on here, right? When you ride a bike, you're pedaling. The pedals are attached to the main sprocket, right? Just a gear. And so they're giving us the radius of the pedals, right? The length of the lever, essentially, that's the pedal, and the radius of the front sprocket. Okay. So how do I calculate the mechanical advantage of that wheel and axle? So all it is just the ratio of the radii, right?
Set up a ratio.
Mm-hmm. Set up a ratio, right? And remember that when we're calculating an actual mechanical advantage, it's always going to be the ratio of the output force divided by the input force, right? So for example, if I input 50 pounds of force and I get back 150 pounds of force, then it's a mechanical advantage of 3. Actual mechanical advantage of 3, right? 150 over 50. Multiplied my force by a factor of 3, right? To get in theoretical mechanical advantage or an ideal mechanical advantage, we're going to take the ratio of the distances, right, that are involved, but it's going to be the opposite, right? Because we should have to get a multiplication of force, we should have to push through a longer distance, right? And so we'd say input distance instead of output force divided by input force, which is actual mechanical advantage. We do input distance over output distance, right? So we'll call it TMA.
Can you draw pictures to let me know?
Sure. Yeah. So here's the pedal. Right there's the center of the pedal, and there's the gear. Right. And then the chain is just attached to like that, right? It just goes around the front gear. Okay, but for now, that front gear, what's the input distance? Well, that'd be, the input's gonna be the pedal, right? Because that's what you're pushing on is the pedal. Does that make sense?
Yeah.
Okay.
So it'd be 183.
So 183.8, right? So the first simple machine mechanical advantage is going to be, the arm, essentially, and this is just a lever, isn't it? This is just going to be the input arm, right? Or the effort arm, they call it arm. So 183.8 milliliters divided by the output arm or the output radius. That's just going to be the radius of the gear that's actually doing the work. It's turning the chain. Okay. 76.9. So that's going to give us a mechanical advantage greater than 1. Makes sense, doesn't it? Right? Because the pedal is longer, so I should be able to multiply my force using that first simple machine, right? So I'm multiplying the force that I apply to the chain. Okay, what about the second wheel and axle? So over here now the chain is driving this rear sprocket, right? So now the chain driving the sprocket, that's the input, isn't it? Right? And then the output is the wheel pushing on the ground. So then back here there's this big wheel that's against the ground, right? Yes.
To convert meters from kilometers to divided by about.
there's 1,000 meters in a kilometer. Okay, so then the second one, so now TMA two is gonna equal the input radius, which is small, it's, what, 30.1 millimeters? Divided by the radius of the wheel, which is big, 307.2 millimeters, so the units all cancel, of course, and so we end up then with the overall mechanical advantage, just the product of those two. So the theoretical mechanical advantage,
Wait, so why did you do 76.9 and first one was 30.9?
well, because the input is, I'm applying the force to the pedals, so that's gonna be the input lever, or the input radius. The output is transferred to the chain. So I pushed the chain, now the chain is carrying the force. Remember, the tension in the chain now carries it, right?
So the rear sprocket is the blue circle,
So the rear sprocket is the orange circle,
and then,
right? So then the chain is now transferring the force to the sprocket, so that's the input for the second simple machine.
well, what's the gear attached to
The gear's is attached to the wheel.
which one is that?
This is the wheel, the tire that's
So
on
the
the ground.
gear attached to it.
Yeah.
It's
Just like
the
on a,
rear sprocket.
just think like on a 10-speed bike where the wheel, the chain, goes around the rear sprocket.
It does for the gear.
Right, and you can switch, right, you can change up the ratios by flipping the gears, right? We didn't have that option in my old problem, but you see what I'm saying? So this is, the chain is it's turning this gear, which is attached to the wheel. Here's the spokes on the wheel, right?
Yeah, but I thought so the wheel has a radius of 370 millimeters.
Right, so that's
And
the
then
output
The
radius.
gear attached to the wheel has a radius of 30.1 millimeters.
Mhm.
Which one is that? The gear attached to the wheel.
That's right here. This is the gear. This little distance right there.
Wait, but then why is that different from
Well, because you think about the well, okay, yeah. Think about how the force gets transmitted, right? There's two machines going on. So the first machine, it's human power gets transmitted to the chain, right? So then going into the second simple machine, the chain is driving the second wheel, so that's the input, and the output is the wheels pushing on the ground, which makes the bike go forward. Does that make sense? So you got to kind of think of the path for how the force is. Ultimately, we want the force, your force, to be transmitted to the ground, so you can go someplace. But in the process of doing that, we're going through the middleman of the chain.
I'm sorry, could you
Sure. Yeah, so this is, okay, here's pedal. This blue gear right there is front sprocket. So this is rear sprocket, this guy right here, right? That guy right there. That's rear sprocket, and then this guy right here is wheels. Okay? Does that make sense? Okay, so then we're gonna find the product, but we're not quite done. If the bike only has an efficiency of 95.9%, remember then that efficiency is the ratio of actual mechanical advantage over theoretical mechanical advantage, right? So to find the actual mechanical advantage, we'd have to multiply the theoretical mechanical advantage by the efficiency. So we'd have the product of, we have three things. We have the product of first theoretical mechanical advantage times the second theoretical mechanical advantage times
And that's the.
0.959.
So if it was 100% efficient, just timesing those two would be, it's mechanical.
Right, exactly, right. There's a little bit of loss though in the gears and the friction with the chain and everything, and so then that's gonna give us the actual, mechanical advantage then. And then if we wanna know what the output force is, we'll just multiply what we get from the product of those three things, 1, 2, 3, by the input force of 449.
So-
And then that's joules, right?
Well, no, it's a force, so it's gonna be newtons.
Okay.
So if the answer, when you times the two theoretical mechanical advantages, that's how much force is being put if you're putting in 1 Newton. Got it.
Times the efficiency, right.
Yeah.
Yeah.
So if you put 1 Newton of force, then just timing those two would be our answer.
Yeah. Yep, exactly.
Well, and then
Yeah.
you,
And so what's gonna happen
and then
is,
you times that by.
you can see right away that this second theoretical mechanical advantage is really small. And so a bike is not a force multiplier, it's a speed multiplier, right? At least in this gear, right? We're pushing with an abundance of force, but we're getting back from that extra speed, extra distance, okay? Make sense?
Yep.
Okay? Moral of the story, you multiply the mechanical advantages to get the overall mechanical advantage for a compound machine. All right, another one. Can you tell me which one you want to look at?
So the answer was 105.
Is that what it was? Should we try it?
Wait, three.
Yep.
What do we need?
Yep.
Wait, so when you multiply.
Oh, it's
When
not.
you multiply it by the efficiency,
Mhm.
minimum,
Multiply by the efficiency, yeah.
do you leave it in that form or do you do like 0.95?
Point, yeah, no, you have to write it as a decimal, 0.959, yeah. So let's go back and, let's try this real quick. We gotta make sure we get the right answer. So we can do this all in our calculator.
I did my own well.
Oh, okay.
But I'm doing.
So I'll write this on the calculator in a way that, so you can see what we did.
Make the two equations and then you divide the two? Or you times the two?
So here's what I'm gonna do. I'm just gonna say the quantity 183.8 divided by 76.9 times the quantity 30.1 divided by 307.2 times, what was the efficiency again? 959 times 0.959 should give me the overall mechanical advantage, which is that.
Yeah.
Okay.
And you times it by.
440.
Right, so that times
Uh,
449 is 101, yeah.
Oh, I thought it was your same times it by.
Oh, no.
Okay, so 101, should we try that one?
Yeah, we should.
See if it works. So I don't think you multiplied by 0.959.
I didn't.
Yeah.
Sorry.
That was the issue. There we go. Okay? Good. So let's try the next one. Do you want to do this one or do you want to skip up? Let's just look at all of them. So this is sliding up a ramp, determining pushing force. This is sliding up a ramp, determining ideal mechanical advantage. Actual mechanical advantage. Was there one that, could it have asked you for efficiency too? I can't remember. Okay, so I fixed them. There shouldn't be units. No units, yeah. I think did it want newtons on one of them? Okay, right. Yeah, there aren't going to be a mechanical advantage is a ratio of the same, right? It's gonna be unitless.
Well, I was thinking percent.
Oh, I gotcha. The ones that ask for like efficiency, this is kind of cool. You can put them in either as, so if the answer is 57%, it will take 57% or 0.57. Either one will work. Okay. So which one of these do we want to look at?
I think we did the van sliding, like someone sliding with box on the ramp. Like if,
Okay.
we do that when you were doing it. I mean, if you wanted to do both.
Okay. Let's just look at it one more time. Let's see.
Do I need to convert that to meters per second?
Yes, always.
So let's divide times by 1,000.
Kilo means 1,000.
Yeah, so times by 1,000.
Yeah. Number 4. Okay. Okay, this is going to be a pretty quick one. Yeah. This one is what?
So you multiply the mass times the vertical.
Actually, this one has nothing to do with mass or force, because it's an ideal mechanical advantage, a theoretical mechanical advantage.
1.74.
Yeah,
Sure.
so 8.01 divided by 2.41, right? Is that what you got?
Well, yeah, I was looking at that.
Right, but I mean, you did, but that's what you did on yours. So whatever that is, that's our answer, right? Because it's just the ratio, all this is just the ratio of, what's this doing? There we go.
Is that the same?
Yes. Well, they're different questions, so no, didn't say that. So on this one, it's just gonna be length of the ramp divided by height of the ramp. 8.01
On that one,
divided.
if they want the actual mechanical advantage, you just times it by the amount of force that they're pushing.
Right, so the actual mechanical advantage, that's output force divided by input force. Now, what's the output force gonna be?
Wait, for which one?
Yeah. So what do we get here? How many sig figs?
We put 8.07. You just divide it like that for that.
Oh, I did 8.07, you're right. What was I doing? So, so 3.32? Yeah, okay. Okay, so was it which one, number 3 wanted actual?
Well, my number 4 does.
Oh, okay, so they're kind of random. My 5 does. Do any of them ask for efficiency on anybody's? They might ask for that too? I think maybe I had it sort of random.
Mine, no.
Okay, so actual mechanical advantage, that's gonna be just output force over input force, but what's the output force? In other words, absent the machine, what's getting accomplished here?
Moving it up 2.47 meters.
Yeah, so I'm lifting the load up 2.47 meters, right?
So it's the mass, the weight.
So the weight,
times
the weight of that mass.
Yeah.
So what's that gonna be? 39.1 times 9.8, it's gonna give you the weight in newtons, right?
Times 2.47.
Times 2.47, so that's the output force. What's the input force gonna be?
That.
Oh, actually not times 2.47, sorry. We're just finding, that'd be calculating work, right? We just wanna know what's the ratio of the output force to the input force. So the output force is the weight of the load, what's the input force?
What you're pushing with.
Yeah, pushing force, 160.1. So for this one, all I'd have to do would just be, I would just have 39.1 times 9.8 all divided by 160.1. Everybody see that?
I thought it was input force divided by output.
No,
Oh,
that's, you're thinking of, okay, so ideal mechanical advantage is gonna be input distance over output distance. Efficiency is gonna be input, no, it'd be output too. No, so it's, actual mechanical advantage is always how much are you multiplying the force. So output force divided by input force. Because remember it this way, simple machines are almost always used, when you think of a simple machine, you're thinking of a lever or a crowbar or something, you're almost always using them to multiply force. And so the mechanical advantage is telling you how much you're multiplying the force. Using a crowbar has a really large mechanical advantage because you're multiplying force. Applying a small force gives you a big force out, right? So it's gotta be the ratio of output to input force.
By using the ramp, or increased it by like, whatever that answer is to that question.
So, yeah, so we lifted 39.1, so roughly, what's that gonna be? It's gonna be roughly 390 newtons of output work. We lifted a 390 newton load, ish, divided by 160 newtons, with 160 newtons of input force, right? Which gives us an answer of 2.39. Okay, make sense? So if I wanted to calculate the efficiency given this information, how would I probably do it?
Divide that number by the actual, or the
Divide that by the theoretical. Yeah, I could do that. I could divide it by the theoretical, or I could do output work divided by input work. So if I wanted to calculate the efficiency, I could say my output work is 39.1 times 9.8 times 2.47, right? The weight times the height that's lifted vertically by the machine, right? So 39.1 times, oops, there we go. I'll put them in parentheses so it's easier to see. 39.1 times 9.8 times 2.47 tells me how much work I did in joules, right? The machine did, divided by how much work I input, which was just 160.1 newtons times 12.5 meters, right? And that gives me an efficiency of about 47.3%. It didn't ask that, but
How do you know that's what you divide by? Like, how do you know you don't switch it?
because the efficiency, ideally, we'd have the same amount of work out as in, right? But there's always going to be some loss in the machine, so the output work is going to be reduced a little bit compared to the work you're inputting, right?
Okay.
And so, because the efficiency is always going to be a number between what two values?
0.
0 and 1, right?
Wait, so that number gives you
The efficiency?
electricity.
Yeah. And so it'd have to be, in order to make that fraction less than 1, you know that the output work is always going to be a little bit less because we lost some. Does that make sense? Okay. So how about okay, well, you have to wait a second. I got this. All right. Let's get going. Why is this taking so long? Wow, that's slow.
You bring up an assignment.
I just wanted to- Okay, try. Let's try one of these. It's like two problems. All it really amounts to is I'm adding a couple questions on power, just so you remember the equation. Man, what is it doing? There we go. Try this. So worker uses a pulley system in which 8 segments of rope are attached to the crate. By pulling with a force of 189 newtons, he's able to lift a 459 newton crate. Oh, 710 meters is, that's a little bit off. Whoops. I see something here. What is that? HU. Let me fix this real quick. We'll try this one. Because this is good. This really summarizes everything else that we're looking at. Oh, there it is. try that again. There we go. Okay, 8 segments of rope are attached to the crate. By pulling with a force of 189 newtons, is able to lift the 459 newton crate 7.1 meters in 88 seconds. Okay, so we're supposed to answer all these questions in order, separated by columns. Why don't you come back just a second? Let me go through this stuff first. So we can get the information. So what's the ideal mechanical advantage?
The 189 divided by 8.
Not 189. Remember, the ideal mechanical advantage has nothing to do with forces. That's the theoretical mechanical advantage. That has only to do with the properties of the machine.
So,
That's actual mechanical advantage. Right. Actual mechanical advantage is what really, how much is the force actually multiplied? But theoretically, we shouldn't even have to worry about the forces. So it's just, and we didn't talk much about this. It's just 8. I don't even know if you were here when we talked about it. When we have a block and pulley, remember that the tension is equal. I don't
Yeah,
know.
we did a little.
We did a little bit, but the next, okay, you guys, I didn't do it with this period. I got a good one that I'll pull up from an old, this, you'll like this, hang on. This is good. So, where's that might be it right there, my compound machines.
If there's 4 rope sections, it would just be like the identical one.
Yeah, look at my cool machine I built for the other class. Look at this one. Okay, let's take a look at this compound machine. Oops, I think I can do that. Gotta add that back in. Okay, so let's just zip through this real quick. We got a compound machine here consisting of a wheel and axle, right? The guy's pedaling this wheel, and it's turning, or pedaling a wheel where the pedals have a radius of 15 centimeters, the wheel has a radius of 20 centimeters, right? That's attached to this line that comes down here, and the line is attached to this lever, which is hinged at the far end. He's pulling at one end, and then it's attached via this little pulley here from the middle to this pulley system that's going to redirect the force upward around this pulley, and then it goes to this block and tackle, right? And the block and tackle is lifting this load, okay? So what's the theoretical mechanical advantage of the first part? Well, it's just going to be the ratio of the input distance divided by output distance, so it's 15 over 20, right? 3/4. Agreed? Okay, what about down here? Well, now it's just going to be the ratio of the input arm, right? So it's going to be where's the arm that the force is pushing on? The effort arm or the input arm is the whole thing, right? The line that we're tugging on with our wheel is pulling on the far end of that lever, so the input arm is the whole lever, 4 meters. Now the load that we're driving, that line is attached to the middle of the lever, and so the distance from the output force to the fulcrum is 2 meters, right? Everybody with me?
It wouldn't be the rope on the pulley.
Say it again.
It wouldn't be the rope on the panda. The output.
Well, it is. This is right, but see, this is kind of tricky. It's attached there, and then it goes down around this pulley and back up. The only reason I had to do that is so we could pull up on this thing and cause this line to go down. As you see, we're trying to lift this load. That's all that pulley does, is just changes the direction. Did you ever see that? So then 4 over 2 gives me a theoretical mechanical advantage of 2 for this one, right? Class 2 leverage, like a wheelbarrow, right? Then what about over here? This is the part that I can't remember if we talked a lot about, but now think about this. We've got some tension developed in this line. These are all frictionless pulleys. So what's going to happen if the tension here exceeds the tension there? What's this pulley going to do? No, it's going to roll a bit, isn't it? It's going to just transmit that force equally over the top of the pulley to this line and equalize the load, right? same thing here, same thing here, same thing all the way through this, right? So if they're good pulleys, the tension here, well, maybe not there, but the tension here is gonna equal the tension at any one of those lines over here, right? So what did that do then? This block and tackle, if these are all the tensions that are applied to this load, then think about that. I've got 1, 2, 3, 4, 5 segments, each with a tension T in it. That's the equivalent of having the tension vector multiplied by 5, right? So what's the theoretical mechanical advantage of this block and tackle? It's 5 to 1, because I have 5 segments supporting the load and only 1 segment coming into the block and tackle, right? So that's block and tackle is super easy to calculate theoretical mechanical advantage. Just count the segments, and that's it, right? So this one would be 5, right? Now in our problem, where were we? We were back there, right? Oh, but we were there. That's what we were. Yeah, okay. So what about this one? If our block and tackle has 8 segments of rope attached to the load, what's our theoretical mechanical advantage? 8. Yeah, it's just 8, right? Okay, so first part, 8. What's the actual mechanical advantage? Now that's the forces, right? That's how much is the force actually being multiplied? Well, what's the output force? 459. What's the input force? 189. So the second number has got to be, what is it? So if I divide those, I get 2.43. Okay? What's the efficiency? Well, I could just divide those two, couldn't I? Right? 2.43 divided by 8. What's that give me?
30.4.
30.4. So 30.4% if I want to write it as a percent. And then, okay, now power output. We only talked about this very briefly. We talked about trucks, remember? What's power output? So let's remind ourselves about power. Power is real simple. Power is the rate at which work is done, right? So in physics we say power equals delta W over delta T. I think our book just calls it W over T. So how much work is done in how much time? Right? So a powerful truck, because we've never used your truck as an example when we talk about that. So a powerful truck is a truck that it doesn't necessarily mean it can do more work than another truck. It just means that it can do the work a lot faster, right? So if you're pulling a load up the top of Cabbage Hill, you got a really powerful, you have a truck with a lot of horsepower, it's going to be able to do that work while traveling fast. It's going to be able to get it up the top of the hill going 60 the whole way. You know, a beat up old truck might have to gear down and go in first or second gear and go slower, but it's still going to do the same amount of work. It's going to do it over a longer period of time because it doesn't have as much power output, right? So then what's our answer going to be? How are we going to get our answer here? How much work is done?
Output force times distance divided by time.
Divided by time, yeah. So output work, which is just going to be 459 newtons times 7.1 meters. That's how much work we did. Divided by 88 seconds is going to give us the power output. And what is it?
37.03.
37.03, so 30 to 3 sig figs, it would just be, oh, what was that? Okay. So it's just going to be 37.0, what are my units going to be, remember? No? Watts. Yeah, a watt is a joule per second. Okay. And what happened? Oh, I put too many. I know what it was. We only have 2 sig figs.
Hey, so wait, I was trying to write down the question. How did you find the actual?
Actual is always output force over input force.
So that was like 189 divided by, oh no, 159 divided by 189?
What was that for? The actual?
There we go. You got it.
Yeah.
Yeah.
Okay, so how come? And I had a little note there. You might have seen. If you got this one wrong, I put a little hint in there for you. how come the number of sig figs is 2 and not 1? Why would I pick 1?
Because that's not a measurement.
Okay, exactly, yeah. Because you might think, oh, 8 segments. So therefore the number of sig figs is 1. But you see that that's a whole different thing here, right? That's not a measurement, it's a discrete counting number. So it doesn't apply, right? There's effectively infinite accuracy. If we count to 8, I mean, you can't, it's just, that's it. It's no different than 8.0 than 1,000 zeros. It's always just gonna be 8, right? So that would not impact our sig fig issue. Okay? Make sense? So then this is a super easy problem. If that one made sense, then this one is nothing. Well, it'll make sense when you do. So if I wanted to figure out what the power output was here, what do I do? This,
124.3 times 9.8 times 12.5.
yeah, that's it, right? So it's just gonna be the work done to lift this thing vertically, which is gonna be its weight, so mg times the distance through which it's lifted, times 12.8, divided by the amount of time it takes to do it, gives us power. Okay?
Wait, so, I'm sorry, on the last one.
Mhm.
When you found the power and the difference of work,
If I went back to the last problem, you mean?
yeah,
You're recording later.
so did you just multiply?
Yes, I
it
am.
with-
Yeah, yeah.
Did you multiply the force, the 189 by the distance it went through?
Yeah. Mm-hmm. Yep. Yeah. Work is always force times distance, and the output is what is the machine doing. Input is what are you applying to the machine. Okay. Does that make sense? Does that help straighten things out a little bit?
Yes, recap, really quick. So it's 24.3 times 12.81 times 9.8 divided by 10.1.
Yeah. Yeah. And I hate, in a way, I hate just distilling this down to numbers, but I think that tells a pretty good story. If you can pick the right numbers there, you see what
Yeah,
you see what's going on.
it helps too.
Good stuff.
Can you help me now?
Sure.